the electric field is going to run radial outward from that. So it's always going to be at a distance, at an orientation of 90 degrees. So we're left with E times A. This should be equal to Q enclosed, which is only the Q in this little thing here, divided by the epsilon, the effective velocity.
Shouldn't the arrows be pointed inward?
Well, they are based on what I had over there,
Yeah.
but since I already drew it, I just didn't want to draw it backwards. I probably should. That's why I put a minus and a
Yeah.
plus, and exactly backwards by sort of. So, this is the area of the Gaussian sphere, and then we'll express Q enclosed in terms of the inner radial, the inner conductor, cylindrical conductor. Because again, all the charge is going to be on the outer surface. And as long as it's long relative to this little surface area or this radius, any little collection of charge here is going to be tiny compared to the shaft charge. So, solving for E, E would be related to Q enclosed divided by epsilon A. And Q enclosed we could express as the total, the uniform surface charge density times the circumference of the inner conductor times little l, because that's based on the width of the outer shaft, the shaft length, I should say. All of that divided by epsilon and the surface area of the Gaussian sphere, which would be 2 pi r, same L. Now, in terms of sigma, that's all fine and good, but what I'm concerned with is keeping the Q separate, keeping it outright, explicit, because I'm going to divide it out when I actually, after I get V, and then when I solve for C, I'm going to want to make sure at some point I keep that Q explicit so I can divide it out. So my next step in this was to say, okay, well, I did all of this to figure out how much charge was enclosed. But now I'm going to remind myself that this is in fact equal to the total Q divided by 2 pi r1 large L. And then I've got,
That whole expression equals that?
and then these, no, I gotta make sure everything cancels out. So I can cancel that stuff out there. And I'm left with then an R1. So I canceled out before I brought everything over. Now I've got an R1 over an R1, which I can get rid of, and I'm leaving out epsilon again, so it's the same thing for that. And so what I'm left with then is Q over 2 pi L epsilon, and if this were an air-filled capacitor or a vacuum, epsilon would just be epsilon naught. That would be consistent with our previous calculation. And Q over L is another way of expressing the linear charge density along the shaft of the inner conductor. So this is the same expression we had before, and the electric field is inversely related to the distance from the center of those concentric cylinders.
What was it that you were saying?
Maybe it'd be easier to see it if we knew that the surface charge density equals Q over 2 pi big R1
So let's note, I'll put it over here next time.
Where it says Q total over area, up top right.
So
Yeah, but like, you know, I make the substitution down here.
sigma is
Just a bunch more.
Q total over the area of the inner conductor.
Or the area of the conductor is 2 pi. Sorry.
2 pi R1 big L. And this is also Q enclosed over 2 pi R1 little l.
Let's see.
I was trying to save that shot in that dry marker board space. Irritating habit of doing that. Write big and then squish everything else into the board.
Drop a bit of that column on the bottom. Yeah, where'd the larger?
Well, it's right here, see?
Okay, all right, that's making sense.
Only thing is, I even said it in words, I just didn't write it down. Yeah, so it's inversely related to the distance from the center, as long as you're outside of that inner conductor. So everything kind of looks, again, like a point charge, a line of charge, whatever, as long as you stay outside of it. When you're inside, it's all, everything changes. But when you're outside, everything sort of reduces to like a hollow sphere. It still looks like a point charge as long as you're out, as you're looking from the outside. So if I were to then, I will go ahead and summarize this. So we're left with, if you will, Q over 2 pi L epsilon R. And if Q is negative in the center, it's an inward electric field. If Q is positive in the center, it's an outward electric field. So the direction will depend on Q, but since I'm going to divide Q out, all I care about is the magnitude anyway. So I'm going to point some last piece out here. I'm going to note something about this cylindrical capacitor.
So it's a safe bet to use this specific step for doing a Gaussian cylindrical.
Well, not unless you can remember it.
Good enough?
Yeah, or you're solving it with Coulomb's law. Unless it's somehow given, like, you know, like a part of a plate capacitor. So again, that's why there's a whole chapter on Gauss's law. So note one consequence of this. And that is the distance between R1 and R2 matters. Which makes sense, right? The closer they are together, the larger the capacitance, because the greater the interaction between the inner and outer charges. Also note that it's directly proportional to length. So think about this one. If you wanted to know how long a coaxial cable was, and you wanted to know directly, measure the capacitance and the dimensions of the inner and outer conductor, solve for L. And if you didn't know what epsilon was, then compare two different lengths. Compare a reference length to the length you're trying to measure. Because the capacitances will be proportional to the lengths of the relative lengths of the cable. So that's essentially the idea. So I'll let you guys decompress on that. I'll come back and I'm going to give what I think is an interesting example. Hopefully you'll find it as an interesting example. The rest of you maybe as well, I hope. Which is the application of biophysics of how you might use this as well. And application of biophysics. So let's take a short break and then we'll come back to that.